Radiation is a process in which energetic particles or energy waves travel through a medium or space. There are two distinct types of radiation, ionizing and non-ionizing. The word radiation is usually used in reference to ionizing radiation only, that is, having sufficient energy to ionize an atom. But it may also refer to non-ionizing radiation, for example, radio waves or visible light. The energy radiates, that is, travels outward in straight lines in all directions from its source. We will look more closely into the three main types of ionizing radiation. The first main type of radiation is alpha decay. When a nucleus undergoes alpha decay, it loses an alpha particle. And alpha particles are made up of 2 protons and 2 neutrons. This is also the nucleus of a helium ion. Here we can see what happens to radon when it undergoes alpha decay. At first, the radon particle has 86 protons and 136 neutrons. After emitting an alpha particle of 2 protons and 2 neutrons, the radon turns into polonium with 84 protons and 134 neutrons. The second main type of ionizing radiation is beta particle decay. A beta particle is an electron. When a sodium atom gives up its valence electron to a chlorine atom, it does not mean that the sodium is going through beta particle decay. Beta particle decay occurs when a neutron in the nucleus of an atom decays into a proton, releasing a beta particle. Here you can see lithium-8 with 3 protons and 5 neutrons decaying into beryllium-8 with 4 protons and 4 neutrons. The third main type of ionizing radiation is gamma radiation. Gamma radiation is a high-energy magnetic radiation of very high frequency. That means that it has very short wavelengths. Gamma radiation is produced by subatomic particle interaction, such as alpha particle decay or beta particle decay. This is an illustration of a gamma ray from an atomic nucleus. Nuclear fission is when a highly unstable isotope splits down into smaller particles. It usually takes place in a particle accelerator where an atom absorbs a stream of high-energy particles such as neutrons. Here you can see the chain that uranium goes through while undergoing nuclear fission. The neutron collides with the uranium nucleus, making it break down into krypton and barium, also releasing 2 more neutrons that will collide with 2 more uranium nuclei, creating an exponential chain reaction. If this reaction is allowed to continue unchecked, mass amounts of energy would be released very quickly. In an atomic bomb, the purpose is to use uranium-235 and let the nuclear chain reaction continue by itself uncontrolled. But in a nuclear power plant, the uranium-235 concentration in the fuel is never nearly as big as in an atomic bomb. Also, the reaction is very carefully controlled and monitored. To control the reaction, rods made of neutron-absorbing material are inserted into the reactor to control the amount of neutrons that could collide with the uranium in the reactor. This is an animation of what a nuclear reactor looks like. Uranium pellets are inserted inside the reactor core. then are fired upon the uranium atoms within the reactor core. The uranium atoms split, creating extreme temperatures and energy. The nuclear reactor gets very hot, so it is surrounded by heavy water. This creates steam, which is then fed through pipes to turn a turbine to create energy. The steam is condensed back into water, and it is returned back to the reactor. Managing nuclear waste. There are three types of nuclear waste: low, intermediate, and high-level waste. Low-level waste includes minimally radioactive material, such as mop heads, cloth, and paper towels, that are used in the nuclear station. Intermediate level waste consists of used reactor components, also resins and filters used to keep reactor water systems cleaned. High level waste is used fuel. We are going to look at how the high level waste is dealt with since it is the most dangerous. Storage of used fuels or high level waste after being removed from the reactors by fueling machines takes place in the nuclear station's water-filled pools. After 10 years of being stored in the water, the fuel has cooled sufficiently to be removed from the spent fuel base. The used rods are placed in dry storage containers and transferred to waste management facilities. Each dry storage container is made of reinforced concrete 20 inches thick and is lined inside and outside with half-inch steel plates. This provides an effective barrier against radiation. At the waste management facility, the container is welded shut and ready for storage. Rigorous testing is employed to make sure there are no leaks within the storage container. Long-term storage of used fuel. The Nuclear Waste Management Organization is the leader in Canada in dealing with the long-term storage of the spent fuel. They have advised the government to use an adaptive phased management approach. This includes continued reactor site storage, and then containment and isolation in a deep repository through vitrification. This is the process where the nuclear waste is turned into glass and then stored in stainless steel cylinders inside deep geological repositories. Pictured is the process of taking the vitrified nuclear waste and placing it inside the cylinder before the cylinder is sealed and tested to make sure there are no leaks. Long-term management of low and intermediate level waste. The way low and intermediate level waste are stored is through the Deep Geologic Repository Project, or DGR for short. The DGR is located 660 meters below ground level and looks much like a mine. It is located deep within the limestone bedrock. It is made up of vaults excavated out of the rocks and arranged on either side of a central access tunnel. The location of the DGR makes it a safe place of isolation to store the waste without affecting employees or the surrounding environment.